Okay, guys, we're going to talk about the second derivative and look at its relationship to the original curve. If you recall, the first derivative tells us when the original curve is increasing and decreasing and has extrema, local max and local mins. And for this one, we're going to look at the second derivative, and that's going to tell us concavity and inflection points. Last time we talked about the first derivative and looking at when an original function is increasing or decreasing. I just wanted to let you know and to take note of this slide that is called monotonicity. It's right up here. It's called monotonicity, and that refers to increasing or decreasing. So if you're ever asked in a question to find the monotonicity, literally you just look at the first derivative, it uses the first derivative, and you look at the critical numbers of the first derivative. So don't forget to look at the critical numbers. And critical numbers are two things. They are the zeros and the d and e of the first derivative. So you're looking for the zeros and the d and e of the first derivative. And you're going to analyze the relationship. Okay? On the last lesson, we talked about increasing and decreasing, which is monotonicity. This lesson, we're talking about concavity. Concavity refers to the shape of a graph. We have two different ways that it can be concave. You can be concave up or concave down. Concave up looks basically like a smiley face. You're smiling, your smile is going up. Concave down looks like a frown face. So if you look over here, highlighted in, let's look at this yellow first part. This would be concave up. It's half of a smile face if you look at that. So it's half. And then over here, right to here is concave up. Okay, so we have concave up and concave up. Now, right in the middle there, it changes to concave down. So right here is concave down. Okay, and you can kind of see that part of a sad face. Now, what is it called when it changes from concave up to concave down? Right there. Those are called inflection points. Inflection points. So inflection points. That's where it changes from concave up to concave down. This slide also shows another picture of concavity. We have, and it talks about the secant line. If the secant line is below it, it is concave down, and if the secant line is above the curve, then it's concave up. So you can use whatever definition you want to see the concave up, and then the concave down. This is yet another example or picture of concave up and concave down. You can see that this is part of a happy face, so it's the right part, and then this is part of a sad face. So keep in mind that not all of the concave up, this is concave up, and not all of the concave down will be your perfect pictures of it. It might be partial pieces, and so you can go off the definition of the tangent lines or the definition of the secant lines or the very first slide definition as well. This is also a really great picture of concave up and concave down, and it shows you the intervals on which you are concave up and concave down. So I'll highlight concave down right here, and so you can see it's part of a concave down, another part, and another part, and then concave up on these intervals right there, concave up, and then concave up. Now, the points where you change from concave up to concave down, like right here, changes from concavity here, here, not at E, and here. Those are again our inflection points. And that's where you change concavity. So it's the point at which you change from concave up to concave down. And incidentally, this is the steepest slope. In other words, it's when slope is decreasing or increasing the fastest. So if you're looking at a business, for instance, you are going to want to analyze the inflection points because that's when your rate of change is the fastest, either going down or going up. Okay, so we've already analyzed the first derivative relationship to f. Now we're going to look at the second derivative, but before we do that, I want to go back to the first derivative relationship with f. So the first derivative relationship, let's look at it for this specific graph. So the first derivative is this red one right here. Let's highlight that. This one right here. So that derivative is first positive right to right there, right? So it's first positive, then it's 0. Then it is right here, 0. Then it's negative. And then it's got a 0. And then it goes back positive. So what does that mean for the original? That means the original is increasing, then decreasing, and then increasing. Which means, and you can see that, look at the original over here. I'll use my highlighter. It is increasing, then decreasing, then increasing. And the original function has a max right between here, right here, and a min between where it's decreasing and increasing. And if you notice, the max and min occurs at the critical numbers of the first derivative. Okay, so now let's look at the second derivative relationship with f. So the second derivative is right here, this green line. And the second derivative goes from negative to positive, and then it has a 0. Okay, so put in our highlights. So we go from negative, 0, and then positive. All right, there. That's where it switches. So what is the original curve doing? Well, before this point right here, the original curve is, looks like, concave down. And then after that point, it looks like it is concave up. And in between concave down and concave up, right there in the middle, is an inflection point. So concave down, concave up, and an inflection point. So our second derivative, okay, let's refresh. Our first derivative tells us where we're increasing, decreasing, and where we have local max, local min. Our second derivative tells us where we are concave up, concave down, and where we have inflection points. This slide goes over the definition of an inflection point, and basically it is a change in concavity. So an inflection point is where the concavity changes. Where does that happen? Well, that happens at critical numbers or a critical value. And that's where the second derivative is either 0 or doesn't exist. Okay, so again, we're looking at critical numbers of the second derivative, and we're looking at zeros and d and e of the second derivative. So it's much like what we did already on the first derivative, it's just now with the second derivative. And instead of telling us increasing and decreasing, it tells us concavity, where it's happy and sad, or concave up and concave down. What we haven't talked about is a three-part relationship, and I'm not going to really spend a lot of time on this, but it is nice to know, and it comes in handy sometimes. So if you only have the first derivative, you can still figure out concavity, because remember, the derivative of the first derivative is the second derivative. So if the first derivative is positive, that means, if the second derivative is positive, that means the first derivative is increasing, which means the original is concave up. So there is a relationship between first, second, and the original, if you need that. We have already done this problem in looking at increasing, decreasing local max and local min. And we found it increased and from negative infinity to negative 4/3, and it decreased from negative 4/3 to 0, and it increased from 0 to infinity. And you can see that on the graph down here. But now we're going to look at it for concavity. We can already see the concavity from the graph, or at least I can. If you look at it, you can kind of see where it's concave down, and then it switches to concave up. So it looks to me like there might be a little bit of an inflection point right somewhere in there. But let's go ahead and find it the old-fashioned way. So we're going to find the second derivative. So the first derivative of our function is 3x squared plus 4x. Our second derivative of our function is 6x plus 4. And now we need to find the critical numbers of our second derivative. Well, our critical numbers are two things. They're the zeros and the d and e, or where it does not exist. There is no place that this derivative does not exist. It's a linear function. So now let's look at the zeros. So 6x plus 4 equals 0. 6x equals negative 4. X equals negative 4/6, which simplifies to negative 2/3. So now we're going to make a chart of values. The second derivative and the original. So we have the interval before negative 2/3, 2/3, not 2/6. We have negative 2/3, and we have negative 2/3 to infinity. Okay, so at negative 2/3, that is a 0 of the first derivative, or the second derivative. So we need to test a value. Let's test x equals negative 1. We would plug it into the second derivative, and we are going to get a negative number. So this is negative. Okay, and over here I'm going to test maybe x equals 0. So 6 times 0 plus 4 is 4, which is a positive, so it's positive. So if the second derivative is negative, the original function is concave down or sad. And if the second derivative is positive, the original is concave up or happy. And in between, when you switch concavity, you have an inflection point. And that inflection point right there would be x equal negative 2/3. And you can see that it's concave down, and then it switches to concave up. So it confirms what we already knew. Usually you would do all of the things, find increasing, decreasing, local max, local min, concave up, and concave down, and then combine it all on a picture graph. Okay, so for this one, example number 2, we're going to look at increasing and decreasing monotonicity, local extrema, and then after that, we're going to look at concavity and inflection points. So since we're looking at monotonicity, we need to find the first derivative. So the first derivative, f prime of x, which is our slope, is 3x squared minus 6x. Then we need to find the critical numbers. Which are the zeros, the d and e. No, does not exist numbers. With the zeros, we get 3x squared minus 6x equals 0. Factor out a 3x, and we're going to get x minus 2. We get 3x equals 0. X minus 2 equals 0. We get x equals 0 and x equals 2. So those are our interval numbers. So we're going to cut the number line into 0 and 2. We have before 0, negative infinity to 0, at 0, between 0 and 2, 2, and then from 2 to infinity. And then we're going to look at the first derivative and the original function. So, let's see what we got here. A nice tester number maybe and negative infinity to 0 would be negative 2, negative 1. So you can test x equals negative 1 and you get that the first derivative is positive. Okay, so that means the original function is increasing or going up. In the interval from 0 to 2, I would test x equals 1 and I get negative. So that means the original function is going down or decreasing. Our derivative is 0 at 0. And since our original function goes from increasing to decreasing, we have a max at 0. Okay, interval from 2 to infinity, I would test maybe x equals 3, and I get positive in my derivative, so that means my original function is going up. It's increasing. On this, I have going down to going up, so that's going to be a min. So we have a max at f of 0. I plug 0 back into, this is a max. 0 back into the original, I get out 5. And then I have a min at f of 2. Plug that back into the original, 2 cubed minus 3, 2 squared plus 5. I get out 1. So I have a max and a min. My max, there's my min. Okay, so we know when we're increasing, decreasing, increasing. So basically, our graph looks something like this. And there's a max at 0, 5, and a min at 2, 1. Okay, now let's look at concavity. Okay, so this is example 2 continued. And we're going to look at concavity and inflection points. So we are going to find the second derivative. So the second derivative of x is going to be taken off the first derivative. Okay, so the first derivative again is 3x squared minus 6x. Our second derivative will be 6x minus 6. We find our critical numbers, which are the zeros in the d and e. There is no d and e, but there is a 0. Set 6x minus 6 equal to 0. We get 6x equals 6, so x equals 1. So we're going to make this little chart down here. in terms of 1. So we have before 1, so negative infinity to 1. We have at 1, and then we have 1 to infinity. And we're looking at the second derivative and the original function. So we would do a tester value in, I would test x equals 0 in that derivative, and we would get that that interval is negative. So that means the original function is sad or concave down. Okay, test here, maybe x equals 2, and I get positive. If you're positive, you're happy, you're concave up. At 1, the second derivative is 0. And since this function changes concavity from concave down to concave up, there's an inflection point at x equals 1. Okay, let's test and look at the graph now. Okay, it looks like it got what we did. We have, see a highlighter, we have a max right here, we have a min right here, and we have an inflection point right there. And on the inflection point, you can see where the graph changed from concave down to concave up. And you can see the max here, the min down here, and the inflection point right here. So it has everything that we knew before we even had the picture of the graph. Up to this point, we've looked at mostly cubic or trinomials. Not all problems are like that. And so we're going to look at this one and look at increasing, decreasing, monotonicity, local extrema, max and mins, concavity, and inflection points. So not all graphs are perfect like cubic polynomials. So let's see what happens with this one. This would not be a normal function that you would know what it looks like. So we can go blind. Okay, so first things first, we really need to find the first derivative. So f prime of x. So what do we do with the constant 3? We would bring it down. And then we bring the power down 2/3. And the new power is 1 less, so it's negative 1/3. Because 2/3 minus 1 is negative 1/3. And then minus the derivative of 1x is 1. Now we need to find the critical numbers of this derivative. So we need to find the zeros and the d and e. Okay, let's simplify this derivative. Those 3's cancel, and that's going to be 2 over x to the 1/3 minus 1, which is the same as 2 over the cube root of x minus 1. Now look at that function for the derivative. Remember, this is equal to the derivative. And we have a major problem when x equals 0. It won't exist. 2 does not divide by 0. So our d and e is x equal to 0, because that denominator, when it equals 0, won't exist. And then our zeros, we have 2 over the cube root of x minus 1 equals 0. And we get 2 over cube root of x equals 1. So we get 2 equals the cube root of x. Cube each side to get rid of the cube root. And we get x equals 8. So we have x equals 0 and x equals 8. I don't know if that's going to fit. So let's do our chart over here. So we have x, we have f prime, and we have f. So we have negative infinity to 0. We have 0. We have the interval from 0 to 8. 0 to 8. we have 8, and then we have the interval from 8 to infinity. The interval from negative infinity to 0, I would test x equals -1, because I know the cube root of -1. I put that in there. 2 over the cube root of -1 is -1. 2 divided by -1 is -2 minus 1. That is going to be negative, which means the original function is going down or decreasing. Here, this derivative does not exist. Interval from 0 to 8, I would test 1. 2 divided by 1 is 2, minus 1 is a positive, so this is positive. So this function is increasing or going up. So when we go from decreasing to increasing, we have a min right there. A min at what? F of 0 will be 0, looks like. 3, 0 to the 2/3 minus 0. Okay, and then in the interval x from 8 to infinity, I would test x equals 27. Why is that? Well, I know the cube root of 27 is 3. So 2 over 3 minus 1 is going to be negative. So I'm going down. So this will be a max here. And there's a max at f of 8. F of 8 equals cube root of 8 is 2, squared is 4, times 3 is 12, minus 8, 4. 8,4, if I did my math right. Okay, now we need to find, so we've done decreasing, increasing, monotonicity, local extrema. Now we need to do concavity. So we need the second derivative. So f double prime, I'll put it right here, f double prime of x will be 2 negative 1/3, right, to bring the power down, x to the negative 4/3. And the derivative of 1 is 0. And this is going to become negative 2 over 3x to the 4/3. I want to point out that that denominator will always be positive. So our critical numbers, we don't have any zeros. We just have nothing, but D and E won't exist when that denominator is 0. So over here I'm going to make my chart. So I have negative infinity to 0, I have 0, and I have 0 to infinity. I have the second derivative and the original function. And at 0, it does not exist. Oh, I forgot that on my bottom chart. At 8, it was a 0 for the first derivative. Okay, so I would do a tester value of maybe -1. If I put -1, cube root of -1 is -1 to the 4th. +1, -2 divided by +3 is negative. So it's concave down. Put in tester and 0 to infinity is +1. The cube root of +1 is 1, raised to the 4th power is 1, times 3 is 3, and -2 over 3, negative. So it's concave down. So let's think about this graph. It's always sad. It's decreasing, increasing, decreasing, and it does not exist. Okay, there's something really important about this point right here. X equals 0. It does not exist in the derivative. Remember, the derivative is a slope. How can you have a slope that doesn't exist? Remember the teeter-totter effect? It has a kink. I think it has a kink there. So it is sad always, but it goes down and up and then down. And there's a min at 0, 0 and a max at 8, 4. So let's look at what this looks like. And it fits. Do you see the kink? Do you see the kink right here? Remember, f prime of 0 does not exist. And you can actually see it. But then the slope at 8 is 0, right? Slope right here is 0. And we had a max, and this had a min. So, and you can kind of see how this is sad the whole time. You see it? It's concave down, and then concave down. So it agrees with everything that we found using calculus. Okay, this problem is a little different. Instead of being given a function and having to find when something is increasing or decreasing by using the derivative, we are just given the graph of the derivative. This is the graph of the derivative. So let's see if we can figure it out. All right. Let's see what we have. And this looks like a 0 of the derivative of 1, 2, 3, 4, and 5. Okay. This is the graph of the derivative and the original. Okay. So what happens to the derivative first? Well, for this lower part here, the derivative is negative. So the derivative is negative for the interval from negative infinity to 1. Then at 1, the derivative is 0, right? Do I agree that there's a 0 right there? 0, x values. And then from 1 to 5, the derivative is positive. See all those positive values? So the derivative is positive. And then at 5, the derivative has a 0. And from 5 to infinity, the derivative is negative again. So 0, 2 zeros. Remember, this is the graph of the derivative, and the derivative is 0 there. And it goes from negative to positive to negative. Okay, so what does that mean the original function is doing? It is decreasing, increasing, decreasing. And when you go from decreasing to increasing, you have a min. When you go from increasing to decreasing, you have a max. So now you know where you're increasing, where you're decreasing, and where your max and mins are. Okay, so you know all that. Now, we just have to get through what? Where is our concavity and inflection point? Now this one's a little more tricky. Okay, so we're trying to figure out concavity and inflection point. So we're looking at the original, and we need the second derivative. The problem is all we have is the first derivative. Well, when the second derivative is positive, that means the original function is concave up. But the second derivative is the derivative of the first derivative. And if it is positive, the first derivative is increasing, right? Well, if you look at this function over here, it is increasing from negative infinity to 3. It's increasing. So over here, when is this increasing? It's increasing from negative infinity to 3. At x equals 3 has a max, and then from 3 to infinity it is decreasing, right? And so the original is concave down, and that is negative, and that is an inflection point, and that is a 0 of the second derivative, because the slope of the first derivative is the second derivative, and the second derivative at 3 equals 0 with 3. Okay, let that sink in, see if you can do it. Look back over what I did. Again, there's no homework for this section. You are just going to do some problems about this topic on the final exam.